Welcome to part 3 of section 3.3. Here we'll focus on the rational zeros theorem, otherwise known as the rational root theorem. This theorem tells us all of the possible rational roots of our function. It does not mean that it's giving us any answers of what the roots could be, just that if our polynomial does have a rational root, it will be one of these possible roots that this theorem will tell us. Review. We need to make sure that we understand what a rational number is. Real numbers are a huge set of numbers that just aren't imaginary, but rational numbers are a subset. So if you're rational, you're definitely real. But if you're real, you're not necessarily rational. Check out the first 5 letters of rational. It says ratio. Ratio is a fraction. So any number that can be put into a fraction, a over b, where a and b are both integers and b is not 0, is rational. So a and b are integers, and of course b cannot equal 0. That just means a rational number could be like 1/2, 7, right? 7 over 1, negative 45 over 11. Those are rational numbers. 1.2 is a rational number. 1.3 repeating is a rational number. Anything that's nice or if it repeats. Examples of rational numbers, or examples of numbers that aren't rational would be like pi, root 2, anything with I in it, or some crazy decimal that goes on forever that we can't put into a fraction. So rational numbers are basically anything that can be a ratio, aka a fraction. This is the theorem, the rational zeros theorem. And again, we are defining a polynomial. And in this case, we really only care about the constant term and the lead coefficient. All the other stuff does not matter with the rational zeros theorem. I have it color-coded. So like we're going to call P all the factors of the constant, and we're going to call Q all the factors of the leading coefficient. Then the theorem says that if there is some r that is a rational function, a rational zero of f, it is of the form p over q, plus or minus p over q. Meaning, if we want to list all of the potential rational zeros, we take all the factors of the constant over all the factors of the lead coefficient. This is sometimes also referred to as the P over Q theorem. So we need to list all the factors of the constant, all the factors of the lead coefficient, and make fractions. Here's our first example. We want to list all the possible rational zeros of this quartic function. And so according to the rational zeros theorem, we care about the constant and we care about the lead coefficient. So the constant is -3. You can really just look at it as 3. We don't necessarily care about the negative. We'll put plus or minus in front of everything to take care of the sign issue. But p is all the factors of the constant 3. So the factors of 3 are positive or -1 and positive or -3. Those are all the potential factors of the number 3, or if you want to look at it as -3. Then we need to list all the factors of the lead coefficient. We'll call those Q. The lead coefficient here is 2, and the factors of 2 are positive or -1 and positive or -2. Again, the reason we have to include the plus or minus is because you could get 2 by multiplying -1 times -2. So you do have to include the negatives. All right, the rational zeros theorem tells us that the possible rational zeros are all the fractions of the form p over q. So we're going to take every single p and put it over each q. So I like to just have some sort of order to do this. So I like to take each p and put it over each q first. And I'm going to use the plus or minus in front. So we're going to take that 1 and we're going to put it over 1. So I did this p over this q. Then I'm going to take this same p and put it over this q. So we'll have plus or minus 1 over 2, 1/2. The next one I'm going to do, since I've already exhausted this 1 here, I'm going to move on to this 3, the second p, and I need to put that over each q. So we'll have plus or minus 3 over 1, and then plus or minus 3 over 2. So we have taken each p and put it over each q. All right, now can we simplify any of these values, or do we have any repeats? All right, we can simplify 1 over 1, that's 1, and we can simplify 3 over 1, that's 3. We do not have any repeated values. So lastly, I'm just going to write them all as simplified. So instead of writing 1 over 1, we can just write 1 plus or minus 1/2. Instead of writing 3 over 1, we can just write 3 and then plus or minus 3/2. Again, you do need the plus or minus. So we technically have 8 potential rational zeros. So if this function does hit the x-axis at a rational value, it is one of these 8 numbers here. This next example, we want to list all the possible rational zeros of f of x equals x cubed minus 8x squared plus 4. So this cubic trinomial here, we are going to do the exact same thing. We want to first list our p-values. P-values are the factors of our constant, which is 4. The factors of 4 are plus or minus 1, plus or minus 2, and plus or minus 4. Then we want to list q. Q are all the, I didn't mean to underline that whole term. I really only care about like this 1 here, which is what I want to point out. In this case, our lead coefficient is 1. We don't see it. So listing all the factors of 1, they are just plus or minus 1. When Q's 1, this is fairly simple. All right, so all of the possible rational zeros are every possible P over Q. We're going to move through just methodically. Just find your own way to move through these methodically so you don't miss any pairing. In this case, it's pretty easy because they're all just over 1. So we have plus or minus 1 over 1, plus or minus 2 over 1, and plus or minus 4 over 1. When Q is 1, it's really just the factors of this constant here since they're all over 1. So we don't have any repetitions in our rational zeros, but we can simplify them, so I don't need to write the over 1 each time. These numbers are just plus or minus 1, 2, and 4. So we have 6 potential or possible rational zeros of this function. In this final example, we want to do the same thing. Find the possible rational zeros. So we want to first list p. P is all the factors of our constant. In this case, the constant's 10. And the factors of 10 are 1, 2, 5, and 10, all with plus or minus in front. Then Q is all the factors of the lead coefficient. In this case, that number is 2. And the factors of 2 are 1, plus or minus 1 and plus or minus 2. This one probably has, this is the most that we've done so far. And again, you want to be methodical about putting those P's over the Q's so you don't miss any. So I'm going to take each p-value and put it over both of those q's. So first I'm going to take 1 and put it over 1 and 2. That gives us 1 over 1, which I'm just going to write as 1 this time, and then 1 over 2, which is 1/2. All right, next I'm going to take the next p-value and put that over these values. This one, 2 over 1, is just 2. And then 2 over 2 is 1. We have our first repeat. 2 over 2 is 1. We have already listed 1. So we do not need to list it again. We can erase it. Okay, the next p-value I'm going to do is 5. 5 over 1 is 5, and 5 over 2 is 5/2. So plus or minus 5, plus or minus 5/2, no repeats there. We'll have a repeat though in this next set. I'm going to take 10 finally and put 10 over 1, which is 10, and then 10 over 2. 10 divided by 2 is 5. So we do not need to write that one. So we'll have 10 over 1, which is 10, and then 10 over 2 is 5. So we don't need to write that one again. So in this case, I simplified as I went, which feel free to do that or to not do that. And then I also did not have to write down 2 of them because they were repeats. So note, yes, you might think, hey, here's 4 P's and 2 Q's. I should have 8, like combinations of them, but I actually only have 6 because 2 of them ended up being repeats. The 2 over 2 was 1 listed again, and the 10 over 2 was 5, which we already listed. So if there are any rational zeros of this function, they're one of these 12 rational numbers.